Okay, so my name is Roman Sudarikov, and I am technical lead at ImpulseVitune Amplifier team. ImpulseVitune is Impulse flagship performance profiling tool. My role in the team is to develop performance tuning methodology and define requirements for hardware monitoring logic for rather simple platforms. This talk is jointly prepared with Patrick Wu from Network Performance Group with Intel. We're very grateful for the guys to invite us to have this session here. And the topic I bring here today is hardware level performance analysis of platform I/O. Okay, so I'm working for Intel, so lots of legal. Hope you guys can read quickly enough. Okay, so this is a high-level overview of architectural changes at platform level, comparing the latest Xeon server, known as the Skylake, with the previous generation of Intel server platforms. Well, the description of each platform component and its hardware optimization flow is definitely out of scope of that talk, so I will focus on those which are critical for I/O performance. One of the key changes is replacement of the ring architecture with the new mesh architecture, which significantly improves packet throughput and latency for time-sensitive applications and DNFs, which requires large reads and writes between specific cores. Another noticeable change relates to integrated PCIe subsystem. So Skylake moved away from the unified architecture to split model architecture, which in turn increases aggregating traffic and reduces architecture conflict. Another big changes relates to cache hierarchy. Both size and properties of L2 and the last level cache has changed in Skylake. And it's important to understand those changes to get best performance out of the Xeon Scalable platform family. The three levels of cache are organized as follows. L1 cache remains the same as in previous generation of Intel Xeon processors. L2 caches has increased in size. It's now 1 megabyte. It used to be 10 to 56 kilobytes of private MLC cache. And LLC becomes smaller. Now it's 1.375. So if we, for instance, have 10 cores on the platform, then we will end up around with the LLC of size around 30 megabytes. And the LLC is shared among all the cores on the CPU socket. Okay, so another major change is that LLC becomes non-intrusive on the Xeon processor scalable family. This means that the data that resides in the L1 or L2 caches doesn't necessarily reside in the LLC. So when a piece of data is fetched from system memory, the data will be put in the L1 and L2. But however, the data will not automatically be put into the LLC. The data will be placed in the LLC once it's evicted from the L2 cache. Typically, when the least recently used piece of data is evicted. So, in short, on the Skylake system, LLC serves as a victim cache for upper layers. Okay, so that slides provide kind of summary for cache usage and CPU and I/O interaction, and a few comments on this. So on a very high level, there are two different I/O flows, allocating and non-allocating. Non-allocating flow is used for delivering data to DRAM, and it means that we are not going to allocate LLC entry in the alpha cache. Allocating flow is used for delivering data to the LLC. And it's worth to mention at this point that there are three different options to configure platform for I/O usage models. And I will talk about this a little bit later. Okay, so this is integrated air controller. This is a block which configures and controls all I/O flows on the platform. Well, so a few more words about allocating and non-allocating flows. So allocating flow, this is what we call data direct I/O I/O feature, because we are depositing data that is I/O generated traffic into the last level cache. And it's immediately accessible to the cores that may want to access that data within a reasonable amount of time. And actually, there is a careful management to prevent cache pollution that supplies that we can allow this to happen for certain I/O traffic. The other thing that helps to limit LLC pollution is I/O traffic is allowed to use only is allowed to write only in the two ways of the LLC by default. And that's also configurable for usages that could benefit from more I/O ways in the LLC than the default. And also it's worth to mention at this point that LLC ways can be I/O LLC ways can be written by cores. However, I/O devices are not allowed to write the core ways of the L3 cache. So if I/O PCI write results in the LLC heap, because that line was initially brought to the L3 cache, the I/O write can use that LLC allocation even if it's not in the I/O ways. So okay. So this is table with options describing configuration modes for allocated and non-allocated flow. So on a very high level, we can configure the platform for on the platform wide from the platform wide point of view. We can configure as allocating or non-allocating. Another option is we can configure particular root port in all devices behind that root port to stick to allocating or non-allocating flow. And there is one more usage which becomes available starting Skylake platform, where hardware can look at into the non-scoop bit in the zero header of the PCI perspective and determine if the packet goes to allocated or non-allocated flow. So we are a kind of flexible configuration here. All right, so this slide showing circle diagram with available performance monitoring units. So performance analysis and software optimization have become increasingly challenging due to overall compute system complexity. And existing common technique to solve performance-related issues is based on utilizing of performance monitoring units, PMU. And traditionally, the performance analysis is mostly focused on the CPU core. However, when configuring platform for I/O device or when selecting platform for I/O usage models, it's equally important to track performance from some core. And core is actually everything which resides beside the core. So it's socket interconnects, it's L3 cache, it's PCI Express subsystem, and memory controllers. So cumulatively, there are more than 1,000 performance monitoring events that can help understand micro-architectural activities while running an application. Okay, so here I roughly outlined how PCI Express device interacts with the Xeon family using direct data I/O technology. So I don't want to say this as people already know, just mention that on a very high level, RX part as an example. And then we will discuss each step in details and see how which PMU can be used to track performance at each step of execution. Okay, so this is all about the I/O. The feature allows I/O devices to send the data directly to L3 cache, and then core comes and picks it up out of the I/O ways. And the I/O technology brings two main advantages. It can allow saving in latency and memory bandwidth. It also worth to mention at this point changes in cache hierarchy on the latest Xeon family platforms. So those changes may affect some implicit assumptions software might have about cache being inclusive. And this becomes especially relevant for I/O-intensive applications, which performance heavily rely on fixed usage of DDI feature. Okay, so to the points. Optimizing performance of compute system usually involves going through an iterative process of analysis and tuning across involved software and hardware system components and layers. For system level performance analysis of IO-centric applications like storage or network, in addition to CPU cores, it's equally important to use ARM core. And IO-centric software application exercise and stress multiple parts of the IO flows. So basically, there are three on the very high level, there are three metrics which needs to be observed while debugging performance of IO applications. It's IO throughput, it's a memory bandwidth, and it's socket interconnect transactions. Okay. All right, so let's start from the understanding precise performance. So those executive names in the blue boxes represents hardware counters as a equivalent in the publicly available Intel documentation. So flows, we can divide flows for two directions. Inbound, that flow is from the IO device towards the CPU core, and outbound, when CPU core writes or reads something from the IO device. Okay. So we have dedicated counters to track each transaction, and also it's worth to mention that for inbound writes, we have counters to track both 64-byte line and partial writes. So it's IO and 4 counters we have. So what we can do using those counters? For inbound traffic, we can actually use those counters to calibrate IO throughput. This is the lowest possible level where we can collect performance data. Below that layer is just physical wires. Okay, so using those counters we can collect throughput, and starting the SCADA system we also can map those counters to the end physical device. So what's especially important here to look for is we can control how efficiently IO device works with the Ultra cache in terms of hits and miss rate, and also we can control partial write traffic. And partial write traffic significantly make the great overall performance of the PCIe system. On the another direction, the outbound path, we can monitor both read and writes. Those operations are quite expensive, so it's better to avoid any type of reads, no reads on the sensitive path. As for writes, those operations are used for signaling for updating speakers by the CPU board, and also we can start with SCADA system. We can map those traffic for each physical device. Bandwidth, the Missouri bandwidth. So what type of problems we can learn and solve using those traffic counters coming from the Ultra cache and from the memory controller. So there are a whole bunch of performance issues related to the NUMA locality, right? And those counters from the onboard and company with counters from the CPU core can give an understanding and give a clue which CPU structures basically fails to use NUMA effectively. And also, it's worth to mention that every time we are crossing the socket boundary, we will inevitably hurt performance, just because latency required for request traveling from the UPI controller and back is much higher than latency served from the local cache. We have set counters at the UPI controller at both ends, which can precisely track all traffic coming through those boundaries. Okay, let me provide a quick overview of the Intel tools which may help in debugging performance. So first is Intel Built-in Amplifier. It's Intel flagship performance profiling tool which list of various analysis types and might target both CPU core and how it can provide some understanding of how your application passes through the CPU core pipeline. And it can monitor peripherals like FPGA, NICs, storage, and give some understanding of how efficiently the platform is used. Right, so this is a screenshot from on the very top guideline, traffic shown from the inbound traffic controller. This is overall incoming traffic. Next is shown the DJR-miss rate. And in that particular case, we can see that with the incoming line rate near 10 gigabytes per second, almost half of that traffic immediately evicted from the L3. So that's a sign of definitely applications are valid in terms of communication of core and IO devices. Below is MIO rights given as a timeline service. So we can use that information to, so what we can do using MIO rights. So in general, we need two MIO rights to complete single network packet. So if we have information about inbound traffic and we have overall number of the MIO right counts, then we can divide one by each other and receive packet per second just on top of the hardware counters. If we take into account batching, then using that approach, we can learn how efficiently we are using batching. So if we will have one-to-one or close relationship dividing one by each other, then we definitely use batching efficiently for that particular application. Below is given DRAM value and so interconnect. So it's overall kind of complete picture for IO performance of the network intensive application. Oh, some measures here. Another handy tool to monitor, to use hardware counters is performance counter monitor. It's open source. It works in the counting mode, and it's even can be useful for those who wants to integrate that API to their own application. So this is a screenshot from the tool. Actually, the tool provides in console mode all those metrics in counting mode. Bandwidth collected from the traffic controller and memory and socket interconnect as well. Well, so what is analyzing performance and what's about analyzing performance with Intel tools? So from easy tables, basically we can calibrate bandwidth and we can figure out